Okay, welcome back, PlayBASIC coders. Just doing a quick impromptu check of what I've been doing lately. So I've been trying to fill out all of the blend combinations for any rendering feature that's in the language. Now there's a few more of these to do, but I'll show you the process anyway. So this is the rope demo from the other day. Geez, we lose a lot of frame rate by capturing, but anyway. Okay, so we've got a solid render mode. We can change the screen depth. So we're checking if it's correct within those forms. What you couldn't do before at all, in fact, you couldn't. Well, you could do it with ground strips. Actually, you could do that. The textured strip version, you couldn't do this with. You couldn't render it to a different surface. If I hit the mouse button, you see it's saying solid at the bottom. So I can do a variable alpha blend. That works in any screen depth, right? We can do a 50-50 blend, alpha addition, subtracting. These are all the standard ink modes that PB supports, right? There's an alpha and, there's an alpha or, there's an exclusive or. They generally create pretty weird patterns. Multiply is where the source alpha is multiplied over the destination, and an inverted subtraction, which probably in this case produces the most interesting effect out of all of them. So what this actually means is behind all of this stuff, right? A command boils down to something like this. We've got our interface. We're catching, common clipping things up front. So we do clipping first to make sure that we're rejecting things that are not on screen. If we make it through, we interpolate and clip which pixels we actually need to draw out of that strip, so it may be partly on screen, and we fall through into kind of a common pattern in this old code, which is just using the having one filler per each bit depth. This works pretty well. This actually works surprisingly well by itself, but it's combination heavy. So for every render mode, every screen depth, you would have to have a blend mode, a routine that does that particular operation. Since there's 4 common display depths, that's a problem. Now, I couldn't just ignore this stuff and go, well, oh no, we won't support any of that stuff, but which really has been the case for a long time. I want to make sure that the libraries are consistent as possible. So you set a thing, you render a thing, you get an expected outcome. That's all, really. Anyway, so if we've got a blend effect running, we've got an alpha addition or alpha blend 50. We're making a simple selection here. This compiles down to a comparison actually in C. Whether we use the generic alpha 50 or we use an optimized version for 32-bit surfaces. Now, these pathways are the best because they understand the pixel formats. There's no work lost in translation. We're reading the pixel in a tight way. We're modifying it and writing it back. These generic versions, we're using a function really to read a strip of pixels, do the modification in 32-bit, and then write it back. And the actual performance difference between the two when you don't capture is about 10 to 15%. That's not much, and it's a lot smaller footprint of code. So we can have more of these routines, and we have generalized outcomes. Alpha addition, alpha subtraction, inverted alpha, multiplication, etc. So look at the variable alpha blend, the generalized routine. but a constant telling us what kind of chunk size we want to deal with. So for the strip, we're doing 16 pixel chunks at a time. And the inner loop is just this. This is the whole effect. You don't have to have multiple versions of the effect. No. So we're doing our ground. We're computing our current foreground color, stepping the interpolations forward. They're macros, by the way. Reading the destination buffer. Now, this has been fetched with here. Now, if the destination is 32-bit and we're working in 32 bits, that's a plain copy. There's nothing special about that routine at all. If it's a different surface combination, then we end up with a bunch of, you know, we're moving those bits around for each pixel to make them 32-bit. So if we're reading from a 15-bit surface, so if we're reading from a 15-bit surface, it gets converted to a 32-bit pixel, and then our operation is all 32-bit, and we write it back. And we just do these blocks until the end of the span, and that's the whole processing bit. We're trying to keep in Visual C6, its ability to track registers is a bit like sometimes it'll spill registers out, and things that you want kept in the CPU's bit registers aren't. In a routine like this, you can't really do that. You've got the gradient steps for the RGBs, the actual RGBs here, that's 6 32-bit registers. You only have 8. If you hand roll this stuff, you can schedule when you read memory, when you don't, what's in memory and what's not, you know. That's why I used to write a bunch of these loops in assembly. Alpha plane is the most complicated one, and this is the scalar version, so we could have used MMX, but we've got a pathway for that by itself. So if you don't have MMX, you end up with scalar. This is doing a pair of channels, so we end up with only 2 multipliers. We probably should lay this out a bit different, actually. We probably should do the G channels together, like that. The thinking is that if we have this calculated here, this calculated there, these calculated, some of that data is going to get popped out of registers and put on the stack or put locally. And we want to avoid hitting memory as much as we can through the loop. You know, the cost of reading memory is still quite high, remember. Most operations these days are 1 cycle or less, you know. So we're hoping that it will choose the most appropriate way of running these. What I actually find now is that you're more memory bound than you are operational bound. So sometimes you can come up with clever approaches of doing things, but if you're hitting memory more, then it just doesn't work out. Anyway, for something like this, you know, I probably would have an assembly pathway. You know, have it choose which filler to use. But nonetheless, our subtraction methods here, we're grabbing the 2 channels from the 2 colors, the destination and the source, and doing a subtraction, and then masking it if it's below a certain point. Now, you can eliminate the comparisons. Comparisons generate branch predictions. Branch predictions are quite painful when they occur. every time I try and optimize these out on modern machines, they actually seem like the branches were very well predicted in the first place. So when I talk about combinations and fillers, this is the stuff I'm talking about. For every back end, there's something like this. And the standard fill mode, this is the filler for 32-bit surfaces, where computing the color, writing it to memory, stepping. So we've got one level of unroll of 4 pixels per loop, and then the leftovers done at the end. What I would like to do in the future code is there are parts of the old libraries that have switches, and there are parts that use function pointers to select the routine. That's something else I'm trying to get rid of as well. Just a matter of a bit of tables and sort of preparing the tables, whatever, and then once you've done that, it makes the routine simpler again, because we know what the output pixel format's going to be up front. So anyway, this is what it's all about, you know. So stuff like this can just draw to different surface depths, and you can just switch the blend mode on and not have to worry about what's happening. Look, I would love to have all of those super optimal. In the past, I would have done that. We've gone through and optimized, effects, variations of the effect that's probably no one even used, not even saw, let alone, makes you feel good about those things. But if they're not being used, they're not being seen, and they're not a high priority, then let's just have them be generic. And then if we need them to be improved, if they become an issue for some demos later on, we can expand those things. I don't think that'll be the case. Alright, that'll do. See you dudes. See you next time. Bye.